Hey, Science 10. So chemical energy from these batteries is converted into light energy for this flashlight. The question is that conversion 100%? Or even could it be 100%? I mean, you need to think about that. Is that possible for 100% of the chemical energy in those batteries to be converted into light energy? Ultimately, that's not possible. So let's look at energy efficiency calculations. This is a LED light, so it's about 75, maybe 80% efficient. Where's that other 20% then, you say? Just released as heat. And of course, we don't use a flashlight for heat. So it's really the useful energy that we're talking about. We put chemical energy from the battery in and get useful light, but not all of the energy coming out of this flashlight is useful. Some of it's just wasted heat. We'll talk about that. So this flashlight here, it can never be 100% efficient at converting the chemical energy in the batteries to light energy. And in fact, there's an equation, there's a calculation that we can do to calculate efficiency. That's basically what we're going to be learning in this video, is making sure you can solve efficiency calculation problems. But yeah, let's look at some different types of light bulbs, just so you can have a basic understanding of some of the efficiency that you run into every day. So I'm going to share my screen here, and then yeah, let's look at how to calculate efficiency as well, and a couple laws of the universe as well. But yeah, looking right here, these light bulbs, and we'll take a few notes on this as well as we get going. Incandescent, fluorescent, LED. Let's write a little bit about each, just sort of right beside here. Write it along with me, because we'll also use that formula we were just looking at beside my head there. So an incandescent light, that's kind of the old style. These are still around and you can still buy them, but they're very inefficient, as you'll see. Basically, if we look at the useful, and let's try to spell the word useful correct, why don't we? If we look at the useful energy output of them and basically compare that to or divide that by the total energy input, right? And as we were just saying, there's no way that these can ever be 100% efficient. Well, in fact, incandescent are terrible. When you look at their useful energy output, in other words, the light that they give off, over the total energy you're putting into them, they're only between 5% and 10% efficient. Most of the energy going into an incandescent light bulb is given off as heat. So waste heat is given off up to 95%. I mean, basically, you could call these types of light bulbs a heater, a really small heater. It's about 90% wasted as heat. So yeah, that's incandescent. Okay, so fluorescent is a lot better compared to that, but still not the best. We'll see the best one here in a moment. And yeah, write this out with me, fluorescent light bulbs. Again, your useful energy output, which is really what you're interested in, right? In terms of this, it's a light bulb, so we want light energy coming out. But the total energy, and when we divide that amount, the useful energy output, by total energy input, and yeah, write this out with me, because this is the actual formula we're going to be using today. It comes out to about 40% for some of them, depends. Up to some of the better ones are actually about 75% efficient. So that's not too bad. Still a fair bit of heat being given off by these, but not as much. LED, though, light emitting diode is what that stands for. LED, it's useful. And let's just really focus on spelling useful correct. I know I can do it. Useful energy. Again, the output, think of the output, it's a light bulb, so therefore it's light over your total. And of course, the top number is going to be smaller, right? Because you can never give off more energy than you're putting in. I mean, that just wouldn't be possible, at least in this universe. Total energy input. Again, we just divide those two numbers, so smaller number on top divided by larger number on the bottom. These come out to between 80% and 90%. So some of your fluorescent actually are close to as efficient as LED. And yeah, I mean, each time energy is transferred, and think about what kind of energy is coming in. We got electrical energy coming into these, and each time energy is transferred from one form to another, energy is always lost as heat. And there's actually two laws that we're going to take a look at, two laws of the universe, if you like, the laws of thermodynamics, and you definitely need to know these two laws. So yeah, so let's take a look at these two laws. Okay, so there are first law and second law. Let's take a few notes on this, but I know you can read these on the screen here. So let's first talk about the first law of thermodynamics, and then we'll talk about the second law. Okay, so your first, and indeed, once again, write this down with me. Thermo is just a fancy way of saying heat. Heat dynamics, the dynamics of heat, as heat moves, as heat is transferred. So thermo, heat, transfer, energy transfer. First law, energy cannot be created nor destroyed. Well, that's interesting, right? But now let's write it out and kind of think about it too. Energy cannot be created nor destroyed, only transferred. So that's how energy works in our universe. It's never created, it's never destroyed, it's transferred from one form to another. And of course, you got many different forms of energy, right? So chemical energy, electrical energy, then eventually light energy. And in fact, yeah, with the flashlight, there's actually a couple transfers going on there. So transferred from one form to another. You and I, we take in chemical energy from plants, but then, you know, our body has to transfer that, has to digest that into a chemical energy that we can store in us to our own glucose, basically, right? So that's the first law. Well, here's the second law. With each transfer, energy is lost as heat, basically. And this is what we really started with the video here. So the first law, the second law of thermodynamics. Nice little line, beautiful, beautiful. So our second law, with each transfer, and energy is always being transferred, especially by our machines, right, that we use in our technological society. With each transfer, energy is lost as heat. I mean, think about it. If you are driving a car, the motor heats up. And yeah, in Canada, we like to have the heat in our car, but the real purpose of the gasoline is to move the car. It's to actually not heat the car. You're mowing a lawn and your lawnmower is going to be heating up. The purpose isn't to heat up the lawnmower. The purpose is to have useful energy to move the blade, right? So energy is always being transferred from one form to the other, but every time that happens, it's always lost in heat. There's always a little bit or sometimes a lot lost as heat. It can never be 100% efficient. Never can have 100% efficiency. That's just not possible. All right, so let's actually take a look at think about these two laws in terms of the efficiency of any of the machines in our society, right? And that's everything from light bulbs to cars to lawnmowers, and just kind of think about what those things do in terms of their useful work, right? That's really what you want to focus on. Let's just take a look at that a little bit. A couple examples here. All right, so efficiency in the second law of thermodynamics. Well, first of all, your useful energy output, the energy that does the useful work. So we take electrical energy in this case and turn it into light. But there's still going to be some heat lost. So your total input is always greater than the useful output. And there's, again, always waste heat every time there's a transformation. Look at these cars here. Think about the total energy input, what type of energy that is. Okay, so that's chemical energy in the gasoline. And the useful is motion. Well, again, cars give off a lot of heat, a lot of noise. That whole process of burning gasoline and turning chemical energy into energy of motion is actually quite inefficient, and cars do give off a lot of heat and are a great example of, well, the second and third law, the first and second law of thermodynamics. And again, the first law, the energy can never be created nor destroyed, but it can transfer forms. So that chemical energy in the gas tank there, you know, it came from somewhere. It came from, well, the ground, from oil and gas, right? And that, of course, came from dead animals and dead plants millions and millions of years ago, essentially. And their chemical energy gets, you know, trapped in the ground and then converted over millions and millions of years through chemical reactions into gasoline. Point being, energy is never created, never destroyed. It transfers form. Every time it transfers, we get energy lost as heat. Okay, so how do we calculate energy efficiency? Let's take a look at that now. I'm just going to flip the slide, and yeah, we're going to look at this right here. Here's our formula. Now, what we want to make sure is write this formula out in our notes, and also, you know, how to solve for efficiency, which we actually started with. We already have a good idea of how to do that. But you may have a question that asks you, well, what's the useful output, right? We might give you efficiency and might give you the total input, and you have to solve for that one. Or we give you efficiency, we give you the useful output, and you have to solve for total input. All right, so let's start off with efficiency. And we do express it as a percent, right? So we'll talk about, oops, times, silly, equals. And we have our useful energy. And, you know, your question might give you that in joules or kilojoules. The units actually don't really matter, but they've got to be the same. If you've got joules on top, you got to have joules on the bottom, because on the bottom is going to be your total energy. And yes, just to finish this off, this is the useful output, and this is the total energy input. So you put energy in. Again, make sure if your top is in joules, your bottom is in joules. If your top is in kilojoules, your bottom is in kilojoules. Now the key thing here, though, with we've just created a fraction, right? And the smaller number in this case has to go on top because of basically the second law of thermodynamics. There's always energy lost, so your total's always going to be bigger. Your top number is always going to be smaller. So we're going to get a decimal, right? But to convert it into a percent, you got to multiply it by 100, right? And that's just pretty standard. You've done that when you have a quiz and you get 8 out of 10, and you go 8 divided by 10. Well, that's 0.8. Well, your percentage is 0.8 times 100, which is 80%, right? 8 out of 10 is 80%, and you know that. Give yourself some notes though right now. This must be a smaller number. It has to be, because of those laws of thermodynamics, and just using that hashtag symbol there to say the word number. This must be the larger number. And when you're doing the questions, this can really help knowing this, right? Well, I'll write the word number this time. Must be the larger number. You got to have the same units, right? Whatever the units are, actually really doesn't matter, but they got to be the same units on the top and the same units on the bottom. So if you got joules on top, you got to have joules on bottom. If you got kilojoules on top, you got to have kilojoules on the bottom. Again, think about, you got a light bulb, right? And it's not going to be 100% efficient. And ultimately, some of that electrical energy is going to be lost as heat, and it's the light that's useful, right? So your total is always going to be bigger than your useful that comes out, right? That just kind of makes sense. You've got a big total here, but a bunch of it gets lost as heat. Some useful comes out, and again, that's why, you know, we put our smaller number on the top, larger number on the bottom. Let's also solve, because some of the questions you might run into will want you to solve for useful. So let's just rewrite this and make sure you've got this on your formula sheet. Energy, useful energy output equals efficiency, and as a decimal, so change it back to a decimal here, and obviously you just divide it by 100 to do that, right? Because you timed it by 100 to turn it into a percentage. You change it back to a decimal, your efficiency number, and then multiply this by your total energy. Okay, so that's how to solve for efficiency. That's how to solve for useful energy. What if the question is looking for your total energy input? Again, should be a big number. And to get this one, we take our useful output and divide that by our efficiency. And again, the efficiency, you got to convert it back to a decimal. And, you know, that's fairly straightforward, right? You know, if you have a 90% efficiency, well, that's the same as 0.9. And how did I convert that back? Well, I divided it by 100. Because to go this way, you multiply by 100, right? So if you're converting your percentage back to decimal, you divide by 100. Okay, super cool. So we've got the formula here. We've got the 3 key variables, how to solve for each. Make sure you've got the 3 key formulas, because we're going to start solving some problems. So let's start with a model problem here. Okay, start by reading it, right? A battery charger uses 6,585 joules of electrical energy to charge a battery. Okay, we're charging a battery. But if, smaller number, 5,420 joules of energy are stored in the battery, what's the efficiency of the energy transfer? Okay, so it's not 100%, right? And that makes sense. But how do we solve this? We'll go with our GRASP method. So given, required, you know, start by reading it, but then get these down and write it exactly as you see me doing it here. Analysis, in other words, what formula are we going to need? And then solve it, just plug it in. And then, of course, a paraphrase where we finally write a sentence, but also you're saying the sentence in your mind, and you're doing your last check whether it makes any sense, right? That's really a critical step, because you slow down. You want to slow down throughout this process, but you'll slow down when you write that sentence too. I like to start with what's required. Looks like we're looking for efficiency. And, you know, put down the formula right here. This is required and analysis all in one, but it's a good process if the question is this direct and it's telling us find efficiency. Okay, so to solve for efficiency, useful output energy, right? So your useful output divided by your total input energy. And it looks like it's in joules this time. Make sure they're both in joules, and looks like they are, so there's no conversion required. Now, what are we given? A battery uses 6,585 joules of electrical energy. A battery charger uses 6,585 joules of electrical energy to charge a battery. That's the total input right there, energy. Total input energy. Now at this point, you might want to kind of pause it and just go ahead and solve it. Also take a look, and as you pause it, you know, is this making sense so far? Okay, we're going to keep going here. Our total input energy, right out of the question, 6,585 joules. Our useful output energy, and that is 5,420 joules. Let's go right on into solving this. So my efficiency equals Oh yeah, and you got to multiply this by 100, of course, right? Okay. My efficiency, my useful on top, so the small number on top, 5,420 joules over 6,585 joules. You can take a moment and just make sure this is what the question says. So that's our total that we put in to charge the battery, but only 5,420 basically got stored. So it makes sense. Whatever those are, then multiply it by 100. But let's do that first. Go 5,000. Clear your calculator a lot. 5,420 divided by 6,585. Okay. And it looks like we need 4 significant digits. So we get 0.823. Now we're going to have to multiply this by 100, and it's obviously 82. But let's just write it this way first. And we want 4, so we got to go to our 5th, so we know how to round, right? And ultimately, let's multiply that by 100, but you can do that in your head, right? Like that's 0.82 times 100, so that's 82.30, and either we stay at 0 or we go up. We definitely go up. 31%. We can paraphrase right now. Efficiency for the battery charger, because that's what we're talking about here. That efficiency can never be over 100, can never even actually be 100. And if you do get an answer over 100, then yeah, look at your work basically, because something's gone wrong. So check out your work, and it's always good to check as you're going, not go too fast. Let's try another one. As this one comes up, pause the screen and try to solve it. Okay, so we got a microwave that uses 110 kilojoules of energy to cook a frozen dinner. Measurements show that only 90 kilojoules were actually used to cook the dinner. Okay. So what's the efficiency? All right, so go with your given, required. I've got required just staring at me. We want to find efficiency, and that's going to equal my useful energy divided by the total. And as you write it out, remind yourself, you know, the top number is going to be the small one, and the bottom number is going to be the big one, because we don't want to break the law of the universe. Then, of course, we're going to multiply this by 100. And, you know, we've already done our analysis. We can't jump to solve yet, but we've got a good idea of how to solve this already. And again, just by reading the question carefully. What information are we given? Uses, okay, that's the total right there, because it uses that much to cook, but we only 90 were actually required, basically. Okay, so total energy, 110 kilojoules. Just make sure they're both in the same units. And useful energy is going to be 90.0. Okay, so 3 sig digs, kilojoules. And let's just do our calculation here. So our efficiency is going to equal 90.0 kilojoules, are useful, over 110 kilojoules, and then of course multiply that by 100. But first just do the 90 divided by 110. Make sure to hit clear lots. And ultimately what you're going to get is 0.8181, just 81 repeats forever, looks like. We only need 3, so we're going to stop right here. So we got to look there. If we need 3 sig digs, we look at the 4th one, and either we stay at 8 or go up to 9. We stay. And of course you multiply this by 100, but you know, I think you can see it's just an 81, right? You just move the decimal place twice when we multiply by 100. 81.8% efficient microwave. That's pretty good. And if you think about it, your microwave, yeah, most of the energy goes into cooking the dinner, according to this at least. But on the sides of the microwave, you can feel heat, right? And that's lost, and that's inefficient. What's going on? There's energy being given off by the wires and stuff, some heat. So it can never be 100% efficient. All right, let's try another one. Again, as this one comes up, press pause. Make sure you got your formulas for efficiency so you can solve it. Right, efficiency of a turbine engine is 25%. Oh, we are given the efficiency number, 25%. If the useful energy output, okay, useful is 800 kilojoules, what's the total mechanical energy input? Okay, so given, required, analysis, and write these out and then solve it. Just plug the numbers in. That's the beauty with the solve stage. But required, I want total energy input. It's right there. Don't need the word mechanical. I mean, it is mechanical energy, but it's total energy input. What was the formula for that? We've got that written down over here, right? So your total energy input is going to be equal to your useful output divided by your efficiency as a decimal All right, what information are we given? We are given the efficiency. It's 25.0%. So in other words, we got 3 sig digs there and we got 3 on 800. So just taking a note of that, 25.0%. Divided by 100, or just move your decimal place twice, it's 0.250 as a decimal, right? And we have our useful, useful energy. And that is 800 kilojoules. Well, let's solve. Let's solve for our total. Just use the formula. Take our useful, 800 kilojoules of useful energy, divide that by 0.25. And ultimately, the answer has got to be bigger than 800 is what we want to kind of make sure we're telling ourselves if we end up with the right answer. So hit clear, 800 divided by 0.25. Oh, yeah, makes sense. Big number. 3,200 kilojoules of total, but we only had 3 sig digs. We got to stop there. So we got to write this in scientific notation. 3.20, there's our 3, times 10. This is 1,000, so 10 to the 3, right? And in other words, it's a 3 followed by, 3 zeros essentially, or three places. And, the first place here is the tens, hundreds, thousands. So this just says 3,000 essentially, or 3,200 to be more specific, kilojoules of total energy input. Little paraphrase there, period. Okay, we got one more we're going to try together. And again, try these exact ones on your own later, right? So do the same questions. You want to get the process. That is what is most important, is getting the process for these. An electric motor uses 670 kilojoules of electrical energy to generate 595 kilojoules of mechanical. Okay, so it's electrical being converted to mechanical. Yeah, classic efficiency question. What information are we given? What information is required? Do some analysis. What formula do we need? Which I often like to do right inside of the required, and then solve it. So just plug the numbers in and then your paraphrase. All right, we need to find efficiency. And efficiency equals your useful, which is always the smaller number, energy, output, so what's of use, what's the good stuff, and your total energy input. And of course, we got to multiply that number by 100 to turn it into a percentage. But yeah, what information are we given? We got total energy right there. 670 kilojoules. Again, it looks like we got 3 significant digits. And our useful is 595 kilojoules. We can just plug this in. Okay, so right here, let's solve it. Efficiency equals 595 kilojoules, always the smaller number on top, and always the one that's useful. 595 mechanical kinetic energy. That's very useful for a motor. That's moving stuff. But we had to put in 670 kilojoules. Will make sense. That's following the laws of the universe. And of course, our answer, multiply it by 100, get your calculator, calculate it out. But what you're going to find is it's 0.888. Is it that? Let's see here. 595, I'm sure you will. Enemy divided by 670. Oh yeah, and then a 0 after that. So we got our 3 sig digs right there. Multiply that by 100 or just look at it. 88.8% efficient. Yeah, that's pretty high. Give it an exclamation mark. Okay, Science 10. There's more practice questions in the note package, and go over these exact ones. Do those ones as well to make sure you've got the process for calculating efficiency. Okay, take care.